Hello, so in this part 3 of the Smith chart video, let's have a quick recap on the Smith chart formation, which is described in part 2, and why is normalized impedance is used in Smith chart and how we can mark a impedance on the Smith chart. So let's see. So if we have the transmission line circuits, we will be having the load impedance and we have a transmission line having the characteristic impedance is at 0. So this load impedance will usually be having the resistance, inductance and the capacitance. So in a rectangular coordinate system, resistance will be shown on the real axis, and as the inductance and the capacitance will be shown on the imaginary axis. So here you can see that j omega L is shown on the positive reactance axis and minus j omega c, which is shown on the negative reactance axis. So we have seen in part 2 that how the Mobius transformation is transforming this rectangular coordinate into the Smith chart. So here you can see that how the transformation from the rectangular to the Smith chart is happening. So based on this transformation, it is very easy to identify short and open and the inductance part and the capacitance part on the Smith chart. So based on this, we can easily identify that this is our short, and at this point, at far end of this constant resistance axis will be our open, and as the top is the inductive, the Smith chart top will also be inductive and the bottom will be the capacitive part. So this is how the Smith chart is formed, which is described in part 2 of our Smith chart. And let's go to our part 3. So let's analyze why we have the normalized impedance used in the Smith chart. Because when you analyze the Smith chart, we can see that the impedance, the resistance and the reactance are normalized, and which is shown on this Smith chart. So let's identify why is it so. So in part 2, we have seen that we have the Smith chart was developed to analyze these transmission line problems. So in a transmission line, our aim is to have the load impedance same as the characteristic impedance, because otherwise reflection will happen. That means that if we have a wave transferring through this transmission line and it is going to the ZL, if this ZL is not matched to the characteristic impedance, some part will be reflected back. That reflection is given by ZL minus Z0 by ZL plus Z0. So if this ZL and Z0 are equal, that means that the reflection will be 0. So we can say that it is perfectly matched case. So the Smith chart was actually developed to analyze these type of transmission lines. So in our cases, there are different types of transmission lines. So let's see some example like RG58 coaxial cable. It has a characteristic impedance of 50 ohm, and RG6 coaxial cable, it has a characteristic impedance of 75 ohm. So if we are using the Smith chart for different impedances like 50 ohm and 75 ohm, if the impedance is normalized, we may have to use different Smith chart like Smith chart for 50 ohm analysis and Smith chart for 75 ohm analysis. So to avoid that, what we can do is we can normalize the impedance. So normalization means just dividing by this characteristic impedance. So if we can normalize that impedance, we can use the same Smith chart for any transmission line problem. So whatever be the characteristic impedance, we can just normalize the impedances and we can use the same Smith chart. That's why in Smith chart, everything is normalized. So here you can see that whatever you are seeing on the resistance and the reactance circles will be of the normalized value. So here the reflection coefficient can be given by normalizing. So here you will be dividing everything by Z0, which is the characteristic impedance. So if you divided by Z0, that will be resulting in Z del by Z0 minus 1 by Z del by Z0 plus 1. So this we can see that the normalized impedance. So that is represented by small z. So if we are able to normalize, so even if we are using any 75 ohm coaxial cable or 50 ohm coaxial cable, by normalizing it, we are avoiding these confusions. So we can have a normalized Smith chart and we can use that for any impedance. Whatever be the characteristic impedance, we can use that normalized Smith chart. That's why the normalization came. So this is how the Smith chart will look like. Here you can see that the values are means like how the values are varying in the resistance and the reactance circles. So let's see what is mean by matched or ZL equal to Z0. So we know that if ZL equal to Z0, there won't be any reflection. That is, it is completely matched. So in that case, if you want to represent the impedance, this ZL by Z0 become 1. So this 1, whatever be coming here, which is showing 1 on the resistive line is known as the matched load. So this is how we are identifying the matched load. By normalization, we will be able to make sure that one on the resistance line corresponds to the matched load. So far we have studied what is where the short comes, where the open comes, where the matched comes, and where comes the inductive part and where comes the capacitive part. Next, let's see if we have given any load impedance points, how we can plot that on the Smith chart. So here is a question. Here you can see that given a system characteristic impedance of Z0 equal to 50 ohm, mark the point representing the load impedance of ZL. So what you have to do is you have to first point out what is the characteristic impedance and what is the load impedance. And our next step, so the first step is normalization of the impedance. So what you have to do is normalization means dividing the load impedance by Z0. That is finding out the Z. Just divide 25 plus J50 divided by 50. So it will result in 0.5 plus 1J. So this is the impedance we have to plot on the Smith chart. So this one, the real part will be corresponding to the resistance and the imaginary part or the reactance part will be corresponding to this. If it is plus, that means that this is an inductance, and if it is minus 1J, it is capacitor. So plus means that inductance and minus means that capacitance. So let's see how you can plot on the Smith chart. So let's first consider the scenario of a rectangular plot. So in the rectangular plot, what we will do if we want to plot 0.5 plus 1J, we will be looking for 0.5 on the resistance axis, right? And we will make sure that where the 0.5 comes, and we will be looking for 1J on the reactance axis. So here comes the 1J, and we will be looking for the intersection of both these points, and this will be representing our requirement 0.5 plus 1J. So similar thing will be happening for the Smith chart. So in the Smith chart also, this is our constant resistance circle corresponding to the line. So we will be looking for that 0.5, and this is the inductance line because inductance is on the top part. So we will be looking for that 1J line, and we will mark this point. So this is how we are going to mark that on the Smith chart. So let's try to identify that on the Smith chart. So here means we can try 0.5 plus 1J. So we have seen that this is our, here comes the constant resistance circle. So this is my zero point 0.5. So I have to note this one, this constant circle, and 1J. So I have to look for where comes the 1J. So this is the inductance marking. Here you can see that 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0.6, 0.7, 0.8, 0.9, and 1. So this is the inductance part. So if I draw this line, you can see that here comes the intersection point, this intersection point. So this will be corresponding to 0 0.5 plus 1J. So just mark this point. So this is how we are identifying the point on the Smith chart. So I hope you get some idea about what are how you can identify a point on the Smith chart. So in our upcoming videos, we will be discussing about what is meant by moving towards the source, load, and how you can identify ZW or return loss from the Smith chart, and what are the different impedance matching techniques which can be implemented using the Smith chart, like quarter wave matching, single step matching, T-pi network matching, etc. I hope you get some idea about what's the Smith chart and how you can mark the point on a Smith chart. Thank you.